what you are seeing is this end is that particular point is your source. So now I am choosing a crystal and it is about one particular axis, is oriented. So now that is the position of the crystal. This is the source, and then there is a very faint blue circle. That is your sphere or sphere of reflection. So now you can see these points, some of them are bright and some of them are dull. I will explain you why some are bright and some are dull. Those points are the corresponding reciprocal lattice points of this particular crystal in a given reciprocal lattice plane. The crystal is oriented in one direction, so it says it is 0, 0, 1 plane of reciprocal lattice. So now you see when a particular point is crossing the reciprocal lattice, this your sphere, it is diffracting. This point is exactly the straight line from the beam, and this beam is enormously intense. So when we learn when we discuss about X-ray diffractometers, we will get to know we don't use anything which goes straight. So what we do is we use a beam stop, a piece of lead, to stop the direct beam from falling on the detector, because direct beam is very intense. And detector is sometimes placed in such a way that the direct beam can go and hit that. So we place a very small piece of lead just behind the crystal to stop anything going straight. So that is why there is a cross. But you see, now if I start the video, see, whenever a reciprocal lattice point is crossing the blue sphere, it gives you diffraction. And if you try to see, keep your eye fixed on, suppose, this dull spot and see what happens. I am doing it stepwise. See, now the dull spot enters the eval sphere and goes and does not cause diffraction. Right? If you keep eye on that bright spot, bright reciprocal lattice point, as soon as it touches, the diffraction starts. 2, 3 steps, you get the maximum intensity, and when it goes inside, the intensity disappears. So what all steps I have done are snapshots of diffraction image of this crystal. I am rotating the crystal maybe every time by 0.1 degree or 0.2 degree or 0.3 degree. The reciprocal lattice point slowly moves in space. So at one point when it just touches the circumference of the sphere of radius 1 by lambda, it starts to diffract. It may take 3 or 4 frames of 0.3 degree width for that reflection to pass through the circumference. So in 1 to 3 or 4 frames, you will have same spot. Starting with a very small intensity, next one will have slightly higher intensity, third one will have maximum intensity, fourth one very low, fifth one almost nothing, and sixth one 0. So if you try to measure the intensity in terms of electrons, and then you plot number of electrons versus angle of rotation, you should get a Gaussian type of curve. Sometimes some reflections are very sharp and very high intensity. It may so happen that in one frame it is very small, second frame it is enormously large, and third frame it has disappeared. So that also is possible. So that is why we always try to record X-ray diffraction data with a very, very small width. Width means the angle by which you rotate the crystal. Either you rotate it by its own axis, which is called phi, or you keep the crystal like this and rotate it like that, which is omega. Normally we do phi and omega scans, but then it is possible to keep the crystal exactly vertical or exactly horizontal. The angle the crystal makes with the horizontal plane is called kappa. So, three different angles about which one can orient the crystal, two different angles about which one can rotate the crystal, and a third angle, which is the fourth angle, which is 2 theta, is the position of the detector, that also can be changed. Suppose if you have placed your detector somewhere here, exactly the place where I have put my hand, if you have put the detector here, you are technically covering from about 0 degree to about 55-60 degree into theta. So anything comes from here up to this is going to be recorded. This detector is not going to record this or that reflection. So with the position of the detector at about say 30 degree with respect to the beam, it covers from 0 to 60 degree. Center of the detector is at about 30 degree with respect to the beam. If you place the detector like this, straight along the direction of the beam, you get plus 30 to minus 30. So on either side, your maximum 2 theta is 30 degree. But then, if you have a chance to get the detector somewhere there, when this angle is maybe 90 degree, this angle may be 90 degree here, detector is kept there, you record from here to there. So when you place the detector at higher value of theta, you record diffraction data that is going at very high angle. What is going at very high angle? The reciprocal lattice points which correspond to very, very small d values. Very small d value means very large 1 by d. That means it is further away from your sphere. So, if we go back to the presentation, I can then explain. The ones which are further away crosses the UL sphere at a further angle with respect to the crystal. So now, you see here, some of the spots are dark and some are bright. I change it to some other crystal. You see all of them are bright. Right? There is no dark spot. And all the spots which are there, whenever they are crossing that blue circle, is making diffraction. Now I change the radiation. It was done using molybdenum till now. I change it to copper. For copper, that blue circle is smaller because wavelength is larger. So 2 by lambda is the sphere which is like this. So the number of spots that can be accessed has drastically reduced compared to molybdenum. Clear? So here again, if I go back to diamond crystal and one particular thing, one particular plane, the same situation is there, some bright and some dull spots, but the number of spots, the number of reciprocal lattice points that you are seeing is much less compared to what you would get if you just change it from copper to molybdenum. Right? Do you know why this is seen? What is the reason behind it? Can somebody guess the reason behind that?
Interference.
Huh?
Interference.
Interference. What kind of interference?
Both constructive and destructive.
Constructive interference gives you diffraction, destructive interference doesn't give you diffraction. So, there are some set of planes for which there is always destructive interference, and for some set of planes there is always constructive interference, nothing in between. So that is called the systematic absence. Before I go to that, so this is a very simple formula to calculate the total number of reflections n that one can achieve using a particular wavelength lambda for a particular crystal of a given volume. You see, it totally depends on 2 by lambda. 2 by lambda is what? Diameter of the UR sphere. So, the number of spots that can fall inside the UR sphere is the volume of UR sphere divided by volume of reciprocal lattice. So, when you simplify, this n is equal to volume of direct lattice by lambda cube with a multiplication factor of 33.5. So, now using molybdenum radiation, one can calculate what could be the maximum number of achievable reflections. But this maximum number of achievable reflection means the maximum resolution that one can achieve with molybdenum radiation, not restricted with 2 theta up to which you can collect data. The maximum resolution that one can achieve with molybdenum is 0.71 by 2 angstrom. But we don't go to that. But this number gives you the maximum number of accessible reflections. And if you do it for a given cell, suppose if you just take this as 1000 cubic angstrom, do it for copper and molybdenum, you will see there is a drastic difference. Because in one case it is 1.54 cube, in one case it is 0.71 cube. 0.71 cube makes the number much smaller. 1.54 cube makes this number larger. As a result, the division is giving you a much less number of reflections with copper compared to molybdenum. Okay. So now we just want to go to that systematic absence. If you look at this array of points, this array of point has arrangement of a primitive lattice. If you construct any unit cell, no need to draw here because all these are there in your Stout and Jensen. I have taken the figures from there. I will give you that copy today. These points correspond to primitive lattice. Suppose it is in 2D. So, if you join the corner points and draw the plane, these are 1-1 planes, right? These are 1-1 planes in 2D. And the ones which are drawn here, I am joining this corner to the corner of next unit cell. That means it is passing through the midpoint of this axis. So it becomes 2-1 set of planes. So now you see these 2-1 set of planes are different from 1-1 set of planes, and in between the 2-1 set of planes there is no other plane. In between the 1-1 set of planes we do not have any other plane. So in case of primitive lattice, you will get diffraction from both the sets of planes. If I now change it to a centered lattice, if you just look at this point, 1, 2, 3, 4, you have a center point. 1, 2, 3, 4, you have a center point. So now I am drawing 1, 1 set of planes. So drawing 1, 1 set here means I am joining the corners. No issue, there is no plane in between, so it will meet Bragg's condition. Look at the 2, 1 set of planes. Start here. From there, I am passing through the midpoint of that axis and going to the next corner. So this is a 2, 1 plane. A similar 2, 1 plane is from here going to that. If you consider this as your image cell, this is the second lattice point, you go there. So these dark lines are 2, 1 set of planes. Now who told you that those are corner points and these are center points? I am telling you, no, I will take those as my corner points and that as center point. So if I do so, this is my lattice. So I draw my 2, 1 plane from here, bisecting that axis and going there. So the dashed line is also 2, 1 set of planes. So the distance between two parallel dark lines is d21. Distance between two dashed lines is also d21. But they are same in terms of electron density. If you see the atomic disposition in the dashed lines and the bold lines, they are identical. That means these two are same set of planes with half distance. If Bragg condition is valid for d21, it will not be valid for half of d2. It will not be satisfying Bragg's law. So in this case, in the centered lattice, there will be destructive interference of diffraction, and systematically all 2, 1 set of reflections will be absent. So 1, 1 is there, but 2, 1 is absent. What is the origin of this systematic absence? What do you think? Why we suddenly encountered systematic absence condition for a centered lattice? Which was not there in primitive. A C-centered lattice has an additional translational symmetry which is different from a lattice translation. A lattice translation is one unit translation from this room to that room, from here to up. But this involves half lattice translation. This point is translated here by half along x and half along y. So this non-lattice translational symmetry is responsible for the origin of systematic absence. Then you tell me, then what are the symmetry elements that will give you systematic absence? Like planes, true axis, and if it is a centered lattice, then it is face centered lattice, body centered lattice. In case of monoclinic C centered lattice, all will have some of the other systematic absence condition. Now look at this. If it is 2, 1, there is a systematic absence. What about 2, 2? What about 2, 2? Think about it carefully. When it is 2, 2, that means it is cutting here half and there half, going like that, in between. And there is no other plane which will have same atomic disposition or no atomic disposition on 2, 2. It will not be systematically absent, but it may have a very low intensity. No atom is centered on that plane of 2, 2. So it will have a low intensity, but it will not be absent, because there is no other plane in between 2, 2, 2 planes having the same disposition. So when I say HK, K as odd is systematically absent. So this is a page which, if you don't understand, you will have to memorize, and if you understand, you don't have to memorize. At some point towards the middle of this course, we will be able to derive these conditions using some mathematical tool. But for the time being, we will try to understand them physically. So when it is lattice centering, when I say A, B or C, one face is centered. One face is centered. The centering is giving you one lattice translation along a particular face, and that particular face is designated by H plus K or H plus L or K plus L. So when it is suppose C centered, that means AB face centered. C centered means the face AB is centered. So when it is AB, it is H plus K, which is odd. When it is B centered, that means it is AC face. A and C means H and L. See, H plus L is odd, because the translation is along, in this case it is along A and B, in this case it is along A and C, in this case it is along B and C. So that is how, for general reflections HKL, K plus L odd represents A centered, H plus L odd represents B centered, and H plus K odd represents C centered. Immediately expand it to face centered cubic or face centered lattice. What does face centered lattice mean? All the faces centered. So simultaneously all those three conditions will have to be valid. So for a face centered lattice, all the reflections which satisfies one of those three conditions will become systematically absent. So from a simple cubic to face centered lattice, a large number of reflections will be absent just due to symmetry of face centering. For body centered lattice, the translation is related in all the three directions. It is half, half, half. So from here to there, I am doing a translation half, half, half. So the motion of that atom is in all the three directions. So then the condition becomes H plus K plus L. The sum is odd. So in case of body centered lattice, if it is 1, 1, 1 plane, 1 plus 1 plus 1, 3, odd. 1, 0, 0, odd. 1, 2, 0, not odd. Right? So you can then quickly decide, looking at the HKL values, whether it is primitive or body centered or face centered or one face centered. Now somebody said glide planes. What does a glide plane do? it is a reflection followed by translation. Translation is along one axis, reflection is perpendicular to the plane. So now if I think that a glide plane which is perpendicular to A, immediately that index becomes 0. Any glide which is perpendicular to A, the reflections which are having 0 KL set of reflections will suffer. Now this A glide perpendicular to A can be B glide or C glide. So B glide perpendicular to A means translation is along B. So in set of 0K set of reflections, K odd will be absent if it is a B glide perpendicular to A. B glide means translation along B. So the Miller index which corresponds to B will be odd for systematic absence. C glide perpendicular to A means translation along C. So 0KL set of reflection, L will be odd, not K. And then corresponding N glide, it is K plus L. N glide means translation along both B and C. So K plus L is odd. What is a diamond glide? Diamond glide is 1/4 translation. Then the systematic absence condition is like 4n plus 1, 2 or 3, all of which leads to odd number. But it is 4n plus 1, 2 or 3. So similarly, perpendicular to B and C can be derived. When you go to screw axis, it is one axis. So if it is along B, X and Y change its sign. XYZ becomes minus XYZ. That is why the reflections which are affected are H00, 0K0 or 00L. Because here in mirror case, XYZ mirror perpendicular to B makes it X Y bar Z. Y becomes Y bar. So that we say that it is H0L. Similarly, the ones which change sign, we make those indices to 0 because those are not valid. What is valid is the translation. So screw axis 2, 1 parallel to A means H00 set of reflections are to be looked at, and we will look for H equal to 1. So if we see that 100, 300, 500, 700, 900, all these reflections are absent, it is conclusion that it is a 2-1 screw along it. 2-1 is equivalent to 4-2 is equivalent to 6-3. So similarly, 3-1, 6-1 and all that, you have different systematic absence conditions. These systematic absence conditions, I am again telling you, can be derived mathematically. We will do it at some point. And these systematic absence conditions are absolutely required for determination of space group. See, when we collect a crystal data, we collect it based on the lattice parameters A, B and C with alpha, beta, gamma. And then at some point, if you have sufficient number of reflections at the beginning of your data collection, you may be able to see some of those systematic absence conditions. Because those are applied on general reflections HKL. Those are not applied on some special types of reflections having a special indices. So it is easy to observe those compared to these.